first of all, I think the last quiz is on Thursday. I don't know what number we're on, 6 or 7 or something. That would be the 6th. And then I think that's also the day that you're turning your binders in. And I'll get those back to you the Tuesday after, so you won't have to go without them too long. And then after that, I think the last thing that we have, I don't think, yeah, there's no more quizzes after that. So then it's just getting ready for the final. Our final is Thursday, 12/20 at 11 o'clock in this room. It might be a little longer than the regular test, but not much longer. It definitely won't be. It won't be like a 2-hour test or anything for most people. Definitely not 3 hours. Anybody have any questions about the stuff that's coming up? This is the last of the semester here. Yeah. No, it's going to be kind of the same as the other ones. If it's any longer than the other ones, that'll be just so I can fit in another earlier problem or something. But it really, like, substantively, it won't be any different than the other tests. Yep. No. Yeah, that's finals week. So the week before that is the last week of anyone's classes. Any other questions? Yep. Yeah. Well, that's just, yeah, that should just be part of the, that should just be in the binder along with the other stuff, you know? Yeah, that kind of thing. Yeah. Right. There's a little more information you have to put on it. But yeah, it's just um actually that'd be a good thing to sign for Thursday because that's a good thing to, I think those are always helpful to do. Um, but I don't know. I'm not going to be too picky about how far you get up to with your homework. If you get up to the homework that I assigned for today or last Thursday or whatever, like that's okay. Just be complete with the stuff that you do up to, within a week or something of the due date. Also, if you would, if you're going to have trouble getting your binder the way you want it to be for Thursday, it's fine with me if you turn it in a class late or a week late or whatever. It's better to have it all there than to turn in something that's not done. I won't take off any points for lateness or anything. I'm like, in a way, it just makes my job easier if a few people turn it in late because I don't have as much to do all at once. So that's not a big deal. Anybody have any homework questions, problem questions? So last time, I introduced the TDS equations. And the ones that are most useful for us are the specific TDS equations. So that's T ds is equal to du plus p dv. And also TdS is equal to dH minus VdP. And then we had some simplified versions of this. So if you have an incompressible material, a solid or a liquid, and if you can assume that the specific heat is constant, so that's not always the case, but it's often a good approximation for solids and liquids. Then the change in specific entropy is equal to the specific heat times the natural log of the later temperature divided by the earlier temperature. So what's useful about this form is that you can find the change in specific entropy given only T1 and T2. So just with those two temperatures at the two different instants, you can calculate the change in entropy. Okay, that's if it's a liquid or a solid, if you can treat it as incompressible. Then we also have an approximation if you can assume a gas is ideal. Well, you get a sort of a more simplified form if you can assume that the two specific heats are constant. Most of the time you won't be able to do that. And so the form that we're going to use says the change in specific entropy is equal to S0 at T2 minus S0 at T1 minus R times the natural log of P2 over P1. And so if you can model the gas as ideal, this says that you can find the change in specific entropy, not as easily as you can for an incompressible material, but still given only the two temperatures. And this time you also need the two pressures. So incompressible is you need a little less information. Ideal, you need a little more information than that. But both of them are simplified compared to the overall TdS equations. And so now we have some ways to calculate entropy. We know we can look it up in the table. The definition of entropy. Who remembers the definition of entropy? Okay, so yeah, that's sort of an intuitive idea. Anyone remember, like, mathematically how you calculate it? So definition of the entropy change from state 1 to state 2. The change in entropy is equal to the integral from state 1 to state 2 of, and this is that Clausius integrand dq over t over the whole boundary for an internally reversible engine. Okay, so what that says is, say that you have a blob of pudding, and it starts at this temperature and this pressure and ends at this temperature and this pressure. How do you get from this state to that state? It doesn't matter for calculating the entropy, because no matter how you get there, the way you calculate entropy is you calculate this for what an internally reversible engine would, what would happen if you went from this state to this state using an internally reversible process. And that's how you calculate the change in entropy no matter what process it is. Okay, so that idea of an internally reversible engine or process is built into this. Okay, so now we're finally ready to talk about the closed system entropy balance. Okay, and so this says that for any process, state 1 to state 2, the change in entropy is equal to the integral. Now this is going to look familiar. From state 1 to state 2 of dq over t at the boundary plus some value sigma. Okay, so first let's figure out what these different terms say, and then let's figure out what this says about sort of the second law of thermodynamics. This is like a statement. We can think of this as our mathematical statement of the second law of thermodynamics. This is the second law. Basically, the second law is sort of built into this. So first of all, what's the difference between these two things? This is our definition of the change in entropy. And there's no constant sigma here. And now we have this new thing with a constant sigma here. What's the difference between those two statements? This is important for wrapping your head around this stuff. So this is what you get for this integral for the actual process, not internally reversible. I mean, it could be an internally reversible process, but this is the actual, what's actually happening in your system. And this is called the entropy production. And this sigma always has to be greater than or equal to 0. When would you guess sigma is equal to 0? Well, it's equal to 0 if the actual process is internally reversible. If there's no irreversibilities in the process, then we just get back that definition of entropy, and there's no sigma there. So it's equal to 0 for an internally reversible process. It's greater than 0 for any process with irreversibility. And what this says is no matter what your system is that you isolate, so if everything in your system is reversible, then your change in entropy is going to be the same as you would get for an internally reversible. Well, that's obvious. But if there are irreversibilities in your system, entropy is going to be produced, and that entropy is going to be positive. So you can't ever destroy entropy. Like if you have a process going on, like and you have the system here and the surroundings here, and you calculate the entropy for the system, okay, there's going to be some positive entropy produced in the system, even if overall the change in entropy is negative for the system. The system could have negative entropy, but it's going to produce some of this. And then out here in the surroundings, whatever this is, positive or negative, you're going to produce some entropy there. And so when you add up the entropy of everything together, you're going to get an increase in the universe of entropy by all of those different sigmas. So let's see how that works I'll do an example with a heat engine where it's internally reversible, and then do one where it has irreversibilities. Yep. Well, it's sort of following the same thought process, but make sure that you understand the difference between what the Clausius inequality is saying and what this stuff is saying. All this stuff is like subtle, but it's important for understanding how to do these problems. The Clausius inequality says it says that for any cycle, the integral over the cycle of dq over t all around the boundary is less than or equal to 0. So one of these inequalities, this is a less than or equal to. These new ones this sigma is a greater than or equal to. And we use these things in different ways. Okay, I'm going to erase that. Okay, so let me do an example. And this is just designed to show how entropy production or entropy is produced when a process has irreversibilities. Okay, so let's say there's this heat engine. At the hot reservoir, let's say the temperature is 800 Kelvin. And at the cold reservoir, let's say the temperature is 300 Kelvin. It's a power cycle, so work is done by the system. Heat energy comes in from the high temperature reservoir, and that is, let's say, 1,000 joules. And then we know that heat is going to be lost to the low temperature region. I'm going to call that QC. That's going to have different values for reversible and irreversible. So what's the entropy production sigma? And we're going to do this in two cases. So what's the entropy production for part A? Let's do it for an internally reversible heat engine process. And then second, with irreversibilities present. Okay, so before we do this, what do we expect the numbers to show? What do we expect to be the entropy production for an internally reversible process? 40? No. So the idea is that entropy production only happens if your process has irreversibilities. So if we have an internally reversible process, then there's going to be zero. Sigma is going to be zero. Then if we use values that show there are irreversibilities, that sigma has to be positive. Okay, and so I'll get this in writing in a minute, but one of the reasons that entropy production value is a helpful thing to calculate is because it tells you how many inefficiencies you have. If you have a big value of entropy production, there are probably a lot of places that you can improve your system. Okay, so for an internally reversible process, so what's going to change in our numbers here? We've done an example sort of like this before. If we say that this is internally reversible, we can calculate a value for Q sub C. Okay? And if we say it has irreversibilities, we can sort of specify a value for Q sub C, but it does have a limit on it. It has to have a relationship between the QC that we got for internally reversible. One of those two has to be bigger than the other one. So can you think of, so what do you think, like intuitively, what makes sense about QC? So this is heat that's lost in the exhaust. Would you expect a bigger chunk of heat you add to your system to be lost in the exhaust for a very efficient or a very inefficient system? In an inefficient system, yeah, like if this is a terrible heat engine, just all of this drifts out into the exhaust and no work is done, So the better the heat engine is, the more of this goes to work and the less goes to here. Okay. So we can calculate what QC is for internally reversible. We'll get a number for that. And then we'll just choose some number bigger than that to represent a cycle with, or a process with irreversibilities. And what we're going to see is that sigma is 0 for the internally reversible, and sigma is positive for the irreversibilities. Okay. All right. So how are we going to figure out Q sub C for a reversible system? Yeah, perfect. Yep. So that's based on the Kelvin scale. The way we measure temperature has to do with a relationship between heat transfers for a reversible process, for a reversible heat engine. So QC over QH is equal to TC over TH in internally reversible process. So Q sub C over 1,000 is equal to 300 over 800. And so QC, if you just cross multiply for that, 375 joules. Okay, so that for any reversible power cycle, that is the heat that has to be lost to the cold reservoir. That has to be QC if this is reversible. Okay, so now we're going to use the entropy balance. So the change in entropy is equal to the integral from state 1 to state 2 of dq over temperature anywhere, so anywhere along the boundary, anywhere that there's heat transfer, plus sigma. The definition of the change in entropy is, it's just what I have up above. Change in entropy is equal to the integral from 1 to 2 of dq over t around the boundary for an internally reversible process. Okay, this here is not in the equation for the entropy balance. That term is not necessarily a reversible, internally reversible process. This is the actual process. Okay. But since our actual process in this case is internally reversible, we have, if I rewrite this equation, we have that the integral from state 1 to state 2 of dq over t for an internally reversible process is equal to the integral from state 1 to state 2 of dq over t for our specific internally reversible process plus sigma. What do we know about this integral dq over t for different internally reversible processes? That internal reversibility makes it path independent. Remember, this value has the same, this integral has the same value for any internally reversible process, and that means that these are the same. So sigma is equal to 0. I talked about that a couple classes ago, but we just know that if you are taking your system from state 1 to state 2, you can use any internally reversible process you want to get from that one place to the other, and that integral is going to be the same. Okay, any questions about that? So in other words, for an internally reversible process, entropy production is 0. Okay, so now let's see what happens if you have a real process. So what did we say the deal was with QC? For a process with irreversibilities, is QC bigger than 375, or is that what I said, 375? Bigger than 375 or smaller? So for a process with irreversibilities, QC has to be greater than 375 joules. So let's say 500, nice round number. So we'll say QC is equal to 500. Okay, well, the entropy balance says that the change in entropy in the system is equal to the integral of dq over t around the boundary for our specific process, not an ideal process, plus the entropy produced the integral of dq over t for our specific process The heat that's being added to our system is the heat coming from the boiler, high temperature. So that is, how much did I say? Okay, so that is 1,000 joules. That's positive because it's being added to the system, divided by a temperature of 800, right? And then for our specific system, the heat being lost is 500, and that's at a temperature of 300 Kelvin. And so what do you get for this? Negative 1.54. Is that right? That's 1 2/3 minus 1.25. Negative 0.42. Okay. And what about the change in entropy? Can we calculate that? That is equal to the integral of dq over temperature in the internally reversible case, and we have the values for that too. So for an internally reversible process, this would be, we still have 1,000 coming in at the boiler, so 1,000 divided by 800, minus, this time we're only losing 375 joules at the condenser, so 375 over 300. And what do you get for this? Really? 1,000 over 800. Is that right? Okay. There you go. There must be a reason for that, but it doesn't occur to me right now. So, so if we set up the entropy balance equation, it says that 0, the change in entropy, is equal to negative 0.42 plus sigma. And so sigma is equal to 0.42, and this is in joules per Kelvin. So for a process with irreversibilities, sigma is greater than 0, and that means that entropy is produced. Any questions about that? Mm-hmm. Yeah. Hmm. Yes. Sigma is always going to be zero. Um, it's not, the change in entropy isn't going to always be zero. Even then, the change in entropy isn't going to be zero because remember, the definition of change in entropy uses internally reversible process. And we know entropy is different at different states. So there was something special about the state that the set of states I chose here that made the change in entropy zero. Hmm. Yeah, I see what you're saying. Yeah. And they have to be proportional. I'll have to think about that. I Let's not try to think that through right now. But that's a good point. But the story I want you to remember right now is um, so if you have a reversible, internally reversible uh, process, you're always going to have zero entropy produced. If you have irreversibilities, you're always going to produce some entropy. All right, let's do another example problem. Okay, so let's say that we have an insulated uh, piston cylinder system. And the piston is free to raise or lower. Um, and inside we have water. And it starts as a saturated liquid. Um, and a spinning paddle wheel on the inside increases its internal energy. Until it's a saturated vapor. Okay, and we want to calculate. So first, what is the net of work that's input divided by the mass of our system? And then second, what's the entropy production per unit mass? So per mass. And so what we're trying to find is sigma over m. Okay, well, to calculate the work, how are we going to figure out what the work is? We know that we can't use any entropy equation to calculate something involving work because that never comes up in any of the entropy equations. So let's look at the first law. And it says So the change in internal energy is equal to the heat added minus the work done on the surroundings. Is there anything we can simplify here? There's no Q yet because it's insulated. And so this equation says that the change in internal energy is equal to the negative work. And we can rewrite this as work if we divide both of these two sides by the mass. The work per mass is equal to negative change in specific internal energy, because specific internal energy is just the extensive internal energy divided by m. And so this is negative of specific U2 minus specific U1. And now we can look this up in the table. So look in the table for saturated water. I didn't give you some information here. Oh yeah, this is important. It starts as a saturated liquid at a given temperature. So at 150 degrees Celsius. So we're going to look in the saturated water table at 150 degrees Celsius. And that corresponds to, well, we don't care what the pressure is, but that happens to correspond to a pressure of 4.758 bar. And it gives us a U1 that's equal to 631.68 times 10 to the third joules per kilogram. The U2 of 2559.5 times 10 to the third joules per kilogram. It's the same table, but this is just using the, this is just UF and this is UG. Any other questions about that? Looking this stuff up. Okay, so now that we have that, we can say the work per mass is equal to negative quantity 2559.5 times 10 to the third minus 631.68 times 10 to the third. And that is negative 1,927.82 times 10 to the third joules per kilogram. Any questions about that? Okay, so now for B, we're trying to calculate the entropy production. So we'll use the entropy balance equation. And that says that the change in the extensive entropy is equal to the integral of dq over temperature along the boundary plus the entropy production. And I'm going to divide everything by m just to get that entropy production in the form that we want. So we have the change in the specific entropy is equal to 1 over m times the integral of delta q over t at the boundary plus sigma over m. Okay, well, the change in specific entropy, we can look that up. So from that saturated water table, S2 minus S1 is 6.8379 minus 1.8418. So you get 5.00. This is in kilojoules per kilogram times Kelvin. Okay, so we know the change in specific entropy. What do we know about this second term? So this integral here, is that for an internally reversible process, or is that for our actual process? Our process. And what do we know? What's the first word describing our process in this problem? Maybe the second. Maybe the first one is an. No, insulated. So if it's insulated, there's no heat transfer in or out of our system. And so this integral goes away. Any questions about that? And so we just have that 5 kilojoules per kilogram Kelvin is equal to sigma. So I think, yeah, thank you. Yep. Any other questions? Yes. Mm-hmm. Okay. Yeah, that's a good question. So to think about entropy, so remember that entropy is a property. You can look it up in a table. Okay. So you can look up the change in entropy just based on knowing the beginning and end states. Okay. So you don't know anything about that process when you calculate the change in entropy. Okay. So like you're just getting it out of a table, and that table has no idea what your specific process is. So actual entropy cannot be calculated from our specific process. That has to be some kind of like universal process. And the only thing like a universal process we have is the idea of internally reversible. So entropy itself is defined in terms of taking that integral for an internally reversible process. There's no other way that it could be for that to be a property that has values in a table. Anybody want me to clarify that? You know, um, but then when you go to the case where you're calculating the entropy production for a specific process, then the integral in that case has to be your specific process, because if that was some idealized process like internally reversible, then you'd get the same value for entropy production for everything, and we know that's not the case. So I guess that's about the best I could think of as sort of a way to remind yourself. Well, okay, let's go back to the equations, and so let's go back to the big equations. So really, here are the two that can cause all the confusion. The first one is the definition of entropy. Okay? You can think of this as the equation that lets us put entropy in the table. Okay. Since the table was made before, it doesn't have anything to do with any specific processes. That can't depend on the process that we have. And so it just makes sense that that would have to be an internally reversible process that you use to define entropy. Okay. But now this is not used to define entropy. This is saying once you define entropy, you know, like we could take this integral for the internally reversible process and substitute it in here. Okay. But this equation is what lets us calculate the entropy production for a specific actual process. Okay. And so if this is some kind of idealized thing that doesn't know anything about our process, then this has to be something specific to our process, or this would be an idealized thing too. So just remember, this is the definition. That's based on ideal stuff. This is how you get your hands dirty and calculate your produced entropy for a specific process. Yeah. Okay, let me do another example. Okay, so let's say we have a gearbox. And it could go either direction. But let's say that we're putting energy in here, and let's say that's 60 kilowatts of work, and then we're getting energy out here, and let's say that's, you know, that can't be any more. It's always going to be a little bit less energy because of friction and all the stuff going on inside. Let's say that's 58.8 kilowatts. And let's say that it's in steady state. So this is what I drew up above, but the power coming in is 60 kilowatts. And the power out is 58.8 kilowatts. And the temperature at the boundary of the box is 300 Kelvin. What's the entropy production? All right, well, this problem gives us rates of work. And so anytime you see work, you know you can't do it all with entropy stuff because that doesn't come up in any of the equations. So we're going to have to start with the first law. Let's evaluate everything per second. I mean, you could also do it. You could do it as a time rate of change version of everything, but let's evaluate per second. Then the first law says the change in internal energy is equal to the heat coming in minus the work being done. Do we know anything that'll let us simplify this? It's steady state. So what does that let us cancel? Yeah, there's no change in U. And so this says that the heat coming in is equal to the work going out. And now the work going out, let's think about that. So W is equal to, we have one work, work coming in and work going out. The one going out is the positive. So that's positive 58.8. This is in kilojoules now. The work coming in is negative, and that's 60. And so W is equal to negative 1.2 kilojoules. And so Q is equal to negative 1.2 kilojoules. And now we can calculate the entropy production. So we'll go to the entropy balance equation. The change in entropy is equal to the integral of dq over t around the boundary plus sigma. And now there's something we can simplify here, just like there was in the first law, because this is steady state. What here goes away because of steady state? Yeah, the change in entropy is zero because entropy is a property and properties don't change in steady state. So this is zero because of steady state, same as this. Anything you can look up in the table in a steady state process doesn't change. Okay? And so now we have 0 is equal to the heat. So we have negative 1.2 kilojoules coming in, or 1.2 kilojoules going out. So in the sign convention for the entropy balance, that's still negative. So we have negative 1.2 kilojoules divided by the temperature at the boundary, which is 300 Kelvin. And so we get 0.0 0.004. This is plus sigma. Plus sigma. So sigma is equal to 0.004 kilojoules per Kelvin, or 4 joules per Kelvin. Any questions about that? Okay, let's stop there. So Thursday is our last quiz, and if you can get your binder in on Thursday, bring it in.